Okay, and now we're back. Note that I went back to the script and I have now fixed it so that the chart draws properly. So what I want to do now is I'll revisit this section of the script that talks about building lift charts just to make sure that everybody's clear. So, as I mentioned earlier, we start off, we're creating a binary version of our outcome class that we want to see how well does our model do at detecting that specific outcome class. In this case, the one we care about is Virginica, the species label Virginica. Error number one that I found in my prior code, I was actually using the wrong species ID for Virginica. So I fixed that now. It's actually species ID 3 that reflects Virginica in the original data. So if I look at species names, species ID 2 is actually versicolor. I meant Virginica, so I need 3 to be the value that I use as the basis for building my new outcome class label. So Virginica is what I'm going to try and predict, yes or no, right? So that's what I'm doing here, is building that Virginica column. Next, I'm using the same partition as earlier to define my training and my testing data. It's a 50-50 split, recall. Or rather, you will recall. And I'm building my decision tree on that single outcome class, yes or no, as a function of my 4 predictors with the training data. And again, telling it the method has to be class. This was the second error, one that I caught during the class, the course of our session earlier. This unspecified, it assumes ANOVA, it assumes a continuous predictor. Actually, I want to make sure I tell it this is a class prediction, right? A binary discrete outcome you need to predict. So I build that tree and then I'm going to plot it. There it is. It's a very simple tree. Essentially, the only thing it decides to split on is petal width. Okay, I'm just using the default stopping rules. Again, yours may look different than mine because your randomly sampled training data may be different than my random sample of training data. Okay, now the thing I want to do is with this model I've just built, let's build a lift chart. Okay, and we're going to build it based on the test data set, the holdout data. So the first thing I need to do is I need to figure out measures of the rate at which I detect Virginica species if I rank order observations in the data based on the class probability prediction from my decision tree, right? So I want to start off focusing on the ones that my model is very confident are Virginica flowers. So the way I'm going to do that is I rank order the observations and I start with the first one, and now that I've rank ordered them based on the probability that my model thinks they are the right type of flower, my likelihood of finding Virginica flowers in the first 10% or the first 20% of my data goes up a lot relative to if my data was just ordered randomly, right? If I wasn't using a predictive model to decide where I look. So first thing I'm doing here, I'm recovering those probabilities associated with predictions in the test data for the outcome classes, right? So for each prediction it came up with, what was the probability, or that is what proportion of the training data in that segment of the population defined by that petal width split, what proportion was a 1, right? What proportion of those was it saying Virginica? And I'm telling it, generate a prediction using the tree I just trained in the test data set. And the method here is probability. So give me that proportion. Give me your estimated probability that it is a Virginica for each test observation. Okay, recall, as I was saying in class, what it gives me back, this new, it's not actually a vector, but this new variable is actually a data structure that contained 2 vectors within it. If I look at it, we see it's 2 vectors, right? I mentioned this in class. So this is for each observation, and here's the indices. Notice it's the other 75 indices, the random sample that was left in the holdout data. For each of these observations, what is the probability that it is a Virginica flower? Initially it thinks these are low, and then it gets to a bunch where it thinks the probability is very high. Oh, and here's one that's low, here's one that's low, these ones are high, this one's low, right? So the ordering isn't exactly random at the moment. It's just how are they ordered when I started out with my data set. But the point is, if I just started sifting through these, I might be able to improve my performance, right? If I look here at this default ordering, I'm going to find no Virginicas for a while. It's very inefficient. I'm basically wasting lots of resources sorting through this data and not finding what I'm looking for until I get down here to the 100th observation, and then I start finding them. Obviously, this is very inefficient. Right? So that's what I'm trying to recover with my lift chart, is how inefficient would I be doing this if I wasn't using a model. So again, I only care about the second column here. I don't care about the probability that it is not Virginica. What I care about is the probability that any observation is a Virginica based on my model. So what I'm doing here is I'm overwriting that variable that contains two vectors with just a new variable, which is just the one vector, which is all rows with the second column, this column here. Okay, so I'm just going to have probabilities that it's a Virginica. So I'm overwriting this. So now what I'm going to have, if I look at it again, it's just the one column of values, probabilities that it's a Virginica. Now, first thing we want to do is let's see the rate of detection of Virginica flowers if we rank order the data based on what our tree says each observation's probability of being a Virginica is. Right? So we're going to start with the ones where it's most likely to be a Virginica according to our decision tree. So what I'm doing here is I am overwriting the data set with a new version of itself, where the only thing I'm changing is that I'm ordering rows based on the value in the probability column. Negative means descending order, biggest to smallest. Okay, so this is the probability that came from my predictive model, that something is a Virginica flower. So I'm reordering the rows based on my model. Now what I'm doing is I'm coming up with my measure of the cumulative proportion of observations that I have been able to detect successfully as I progress from one observation to the next in the rank ordered data set. So this is cumulatively, thus far, how many ones have I found? How many Virginicas have I found with each data point as I'm going from top to bottom down the rows, divided by how many are there in total in the data set. So this result is essentially going to be, at this point in the data set, assuming I'm sorting through, going from row number 1 on down to the 75th row, what proportion of all Virginicas have I found thus far? And I'm multiplying it by 100 so that it's not a decimal, right? I want it to be a percent, so instead of 0.5, I want it to be 50%. Okay, so this is my y-axis in the plot. And then I need an x-axis that goes along with it, which is if I was, so this is what proportion of the data have I looked at as of a given observation. So essentially my x-axis, recall, it's given I've looked at 10% of the observations, or 7.5 of them, what proportion of all Virginicas have I found is my y-axis. So I need the x-axis that goes with it. So that's what this is. So this is essentially how many observations am I into the data set at a given point. So am I on the 10th observation? Well, 10 out of how many? There's 75. So 10 over 75 times 100 is the fraction of observations I've looked at so far as of a given point. So that's the x-axis. Okay, so this will give me, I can plot this line, which is essentially what's the rate of detection of Virginica flowers as I progress through the data set using the rank ordering from the decision tree, hence the DT suffix that I'm giving these variables. Now, what do I want to compare it with? Well, if I was using a random ordering, probability theory tells me that whatever the proportion of observations in the data set is that has this value, my probability of finding an observation with that value in any given random draw is equal to that proportion. So essentially, we have 10% of our observations in our data are Virginica flowers. There's a 1 in 10 chance that any randomly drawn observation will be a Virginica flower. Okay, so that forms the basis of our comparison. Essentially, if our data really is ordered at random, then our expectation is we will find a fixed proportion of Virginica flowers as we progress through the data. It'll always be 10%, or every 10 observations we look at, we'll find one if there are 10% of the population is Virginica. Right? In this case, the number is actually higher. I think it's more like a third or something like that. So 1 in 3 observations. So we should find one approximately every 3 observations we look at. We'll find one more. And that's our point of comparison, or assumed point of comparison. Now, of course, if I use an actual random ordering of my data, in any given random ordering, I won't get a perfect line like that because noise will enter the data, and it might be the case that I just randomly by chance happen to find a bunch early on without doing anything, like without using a model. That's luck. If I repeat the random orderings, so if I essentially come up with 50 different versions of my data set where I come up with 50 different random orderings, right? And then I look at the rate of detection as I progress through the observations in each of those 50 data sets, on average across them, what you're going to find is whatever the proportion of the data is the Virginica flower, that's the rate I'll detect them at. So on average, if they're 20% of the data, every fifth one would be a Virginica, or 20% of the, there's a 20% probability that any observation is a Virginica in that case. So the way we actually draw these charts in practice is we assume the random ordering line, right, is equal to the proportion in the data, and that's the point of comparison. So that's what I'm drawing here. I'm calling this ggplot function to make a plot with the test data. I'm telling it the x-axis is the how many data points or what proportion of the data have I looked at thus far, and the y-axis is what proportion of observations do I detect to be Virginica, assuming I've ordered them based on being ordered them using the decision tree. I'm then drawing a line, right? So these x and y values, I'm drawing a line across those data points, and then giving some labels to the axes in my plot. And then I'm going to draw the point of comparison, which is the rate of detection I would expect with a random ordering. So I'm drawing just a line where I'm telling it the slope of the line, the y-intercept, and it should be a dashed line. So I'll draw this. Okay, and this is what I get back. Let me blow this up so we can look at it. So, as we see, we can't do division by 0, and we don't have an observation 0. We have observation 1, so that's why these values are undefined. The reference line is defined because I just drew it, remember. But looking at, what this says is we found all the Virginicas that exist in the data by about 27% of the data. So if we rank order based on is this thing predicted to be a Virginica or not, the probability being high, what we get is we find almost all of them right away, right? We find almost all of them within the first 25 to 30% of the data, and we can stop. We don't find strictly all of them, note. We get actually more like 83%, and then we don't find the other ones till the very end. So our model does really well early on, but then it actually does pretty badly on these last holdout ones. Versus the dotted line is the random sorting, what we would expect to find them, right? How quickly we would expect to discover Virginica flowers in a randomly ordered data set. So we see that the lift over a random ordering, right? It's called a lift chart. So we're saying, in 25% of the population, we find 3 times as many Virginicas in the first 25% as we would if it was a random ordering. So our lift is 3, right? A decile chart is a similar idea, but again, we're just breaking it up into 10 percentiles, right? So in the first 10%, what's the ratio of the height of our line versus a random ordering in the first 10%?